right, everybody. Good afternoon. Full circle, geometric series. I want you guys to remember this here. This is geometric series x to the n. Okay? So I'm going to start this by recalling this particular series here. The terms x to the 0, x to the 1, x squared, that goes on forever. So it's 1 plus x squared plus x cubed. You guys remember this? This is geometric. When do you guys have convergence? So remember, this is a power series. So we have convergence. We got to know what R is. So what's R here? Do you guys know? R is your x. You say, oh, this is my A term, AR squared. Remember, this is the definition. So your radius is x. You get convergence when the absolute value of R is less than 1. You get divergence when it's not. So you get convergence here. So this is my interval of convergence now. -1 to 1. So we already know the geometric series. However, what else do we know about the geometric series? Do you guys recall? Here's a big deal. What is the sum? This is going to be the big deal today. Do you guys remember the sum S? What was that? A over 1 minus R. Is that true? And we already know R is x. What is A, ladies and gentlemen, for the geometric series? Isn't A right here? A is 1. So A is 1. That's this value. So here's what we're getting at, okay? This series can be described as 1 over 1 minus x when your values of x are between -1 and 1. Because this was a geometric power series. We know where we have convergence here. All right, you guys with me on this? Now, this is a big, big deal. You see, because what I can do now is I can write this way. Here's a fact. 1 over 1 minus x is the sum xn, n is 0 to infinity. As long as we know, again, the interval here as well. This is what we say here. So if you really said, okay, what does this actually really mean for us? I'm trying to figure out a color. I can call this f of x because it's a function. So on my left side, that's a function. And so what that means is we can write a function f as a power series. And this has a lot of advantages and to why we do it. So this is kind of the transition now. And you say, what are we transitioning to? Writing a function as a what? Power series. The function here is f. The power series is what you see here, the geometric series. And so we actually use this a lot. You know, we can say, by the way, we can generate using this approach, we could generate other functions. Okay? Like, for example, or note, we can generate other functions. Right? I can say this. If I want to write this as a power series, okay? We're going to write that as a power series. Now you say, well, how do I do that? Well, what I'm going to do is this. I'm going to take this fact here. Tell me, here's how I demonstrate this to students. I'm going to use what we already determined. Okay, I'm going to use that fact, but notice what I did. I changed the letter X to a triangle here. This is the key. So I can put inside here an x squared. If I do that, I put an x squared here, I put an x squared here. Okay, so that means 1 over 1 minus x squared can be described as 0 to infinity x squared to the n. Again, just using algebra. And that's if the absolute value of x squared is less than 1. So on the right side, I can say, isn't that x to the 2n now? 0 to infinity. And the algebra here for this interval, because we can have an interval of convergence, well, that's now the absolute value of x squared less than 1. Or we can say this is where x squared is less than 1, we have the same interval of convergence here. You say, how do we do that? I guess you could do some sign analysis. So, ladies and gentlemen, the function 1 over 1 minus x squared can be described as the sum x to the 2n. This is writing functions as a what? Power series. So with that one tool, I can write a lot of functions as a power series. In fact, you know, they can even say, how about this? They want us to write this as a power series, 1 over 1 plus x even. Okay, they want us to write that function as a power series. So what we can do is we take the function 1 over 1 plus x, and we say this is 1 over 1 minus a minus x. And so now in here, we use that geometric series I just showed you guys here. Right? We take that negative x now to the nth power. By that geometric series, I just demonstrated to you guys over here. This is what we're going to use here. This is what I use. Just plug in that triangle, what you need. You're just going to have to use some algebra now to simplify this. This is negative 1 times x to the n. Properties of exponents from beginning algebra. All right, so here's what you end up with. This is an alternating series. So you just wrote 1 over 1 plus x as a power series. But remember the interval of convergence here. You need the absolute value of that negative x, which does equal the same as what? You say, isn't that negative 1 times x by the product rule? That's supposed to be less than 1, so you're saying the same thing. So your interval of convergence, again, is from negative 1 to 1. All from that geometric series notation here. So you're writing a function as a power series. Writing functions as power series. Another example. Write these functions as power series. Okay? So you start with the function again, and you use that geometric series fact I showed you guys. However, you might say the geometric series doesn't have that 3. The geometric series that we have here starts with 1. That thing starts with 1. You don't have 1. Okay, this is what we're going to use. This is the key right here. So here's what we're going to do. We're going to do what we've done before. How about this? You can actually factor out a 3. Now you have a 1, but now you have plus x over 3. So what I'm saying is you take that number and factor it out. And then we say, well, this is 1/3. 1 over 1 minus x over 3. Did I use the dark green or the light green? I think I used the light green. Right? Now we can use that geometric series. Because this has a 1 there. You guys see what I'm saying? There's a 1? All right. So you'll have 1/3 sum 0 to infinity now, x over 3 to the n. Now we get to use that geometric series form that I gave you guys. I think I messed up here, sorry. Minus the what? Minus. Okay, let me do this here. Yeah. Don't forget, this is a combination of the last two. Now, good, and that has to be a negative, okay? So don't make sure you have that negative sign. There you go. Okay. So, okay, then now by properties of what? You're going to use algebra here. Beginning algebra, properties of exponents. That means you have what? Negative 1 to the n, x to the n over 3 to the n. So you have 1/3, 0 to infinity, negative 1 to the n, x to the n over 3 to the n. Okay, now you might say, what about this 3 that I have here? Well, you can put it back inside your series because of properties of series. Now, this is 3 times 3 to the n, right? And you end up with, ladies and gentlemen, negative 1 to the n, x to the n. This is now 3 to the n plus 1. So this is 1 over 3 plus x. You wrote a function as a power series. But don't forget, what'd you guys plug in? This green thing, this assumes the absolute value of r, which is that minus x over 3, is less than 1 for your interval of convergence here. So the absolute value of x over 3, by the way, is, well, it's going to be this. You can replace this with the absolute value of x over 3, which is less than 1, that whole statement. Okay? Which means the absolute value of x will be less than 3. So the interval of convergence will change here for that function. So the interval of convergence is from -3 to 3. So this is why we wanted to find intervals of convergence, ladies and gentlemen, as well. So you guys have that relationship here. Okay, you guys okay with that? There's a power series on the right there. And by the way, they can say, okay, what if they give you x squared over 3 plus x? Just like the last one, very similar to the last one. Okay, remember this is what we just found. The function 1 over 3 plus x can be written as a power series. So here's what you guys want to know. Again, just a little bit of algebra. This is x squared over, or x squared times 1 plus 3 over x. Notice, you have a power series representation here. We just found out what that was. It's right here. -1 to the n, x to the n over 3n plus 1. So I can replace that with -1 to the n, x to the n over 3n plus 1. But by properties of series now, even though that's not a constant, I can actually put that term inside. So now you say it's inside. It's in my numerator. What do I do with it? The x squared term is where? It's right here, right? So what do you guys do with it? You use beginning algebra. So this is the function x squared over 3 plus x squared. And it'll have that same interval of convergence that we worked on earlier. Okay, just going to double check something here. It's a little different than your book, but okay. Yeah, a little bit different than the book, but that's fine. Okay. Okay, so now I want you guys to note a few things here. So what you're looking at here, remember the general definition of power series. So we can have a sum here. Your definition of power series. 0 to infinity, Cn x minus a to the n. If you guys remember some of these here. Let me double check here. Okay, so here's your definition of a power series. So here's what they're saying here. If you can write F as a power series, so here's your power series definition about A. And then they say if you can write the function F as a power series, then guess what you can do? F prime x, you can differentiate. You see, what this is going to do, it's going to give you other power series. So assuming you could write a function as a power series, okay, then you could differentiate. Now, what does that mean? Well, the derivative of a sum, I'm gonna change colors here. The derivative of a sum, you guys know what that is. Isn't that sum of derivatives? Okay, you guys okay with that? From calculus. And I can pull out constant. So you say, okay, what about this constant? Well, we can pull out the constant, right? And so I have the sum 0 to infinity Cn. Well, what's the derivative? Isn't that n x minus a to the n minus 1, ladies and gentlemen? And this is going to be your derivative. But I have to say, you now have to start here at 1 here. Okay, so I'm going to label this. I'm going to say here, okay, here's property 1. So we could differentiate power series is what we're saying. And we'll see some examples of that. And then 2, if you can write this function as a power series, then we can integrate as well. Because the integral of a sum is sum of integrals, Cn. And then we can pull out our constants again. Cn is a constant. Now we just have to integrate here. And you say, what do I do to integrate? Well, you use your power rule for integration. And then don't forget at the very end, you're going to have this plus c, by the way, So we can integrate as well. And of course, what that means is we're just going to get another power series. There'll be plus a constant c there. And I'm going to put a star here. I'm going to have you guys note here, because remember, every power series has an interval of convergence. So remember, I is that interval of convergence. Even if it's at a point, they call it an interval of convergence. So you start with a power series with an interval of convergence. If you can write that as a function, well, you can differentiate, you can integrate, and they want you to know that these power series will have the same interval of convergence. Okay? So you might say, well, why are they bringing this point up? Because remember this series here, f of x is 1 over 1 minus x, which we wrote as how? Sum xn 0 to infinity. Well, I can differentiate that function. So on the left, I get 1 over 1 minus x squared. You guys know how to differentiate the left side? How do you differentiate this portion here? Yeah, you can actually do this. You could use power rule. Right? So this will be negative 1 minus x to the negative 2, but it's really chain rule as well. Don't forget chain rule. So negative times a negative gives you what? This is 1 over 1 minus x squared. So here's the idea. That's on the left side. On the right side, you say, Mr. Judge, isn't that going to be 1 to infinity d dx x to the n? Yes. And x to the n minus 1? So on the right side, I get the sum 1 to infinity n x to the n minus 1. And you say, well, what's the point? You get a power series. And it's the same interval of convergence as the original. I is negative 1 to 1. So we have another power series there. That's the whole idea. So you're writing these as functions. And then if you said, well, what happens when I integrated? Right? So if you have to integrate that same fundamental power series, right? Well, how do you integrate on the left? Yeah, it's going to be, what is this going to be? Is that U sub? Isn't that U sub? So you're going to end up with what? Negative natural log 1 minus x, I think. Is that right? Yeah, I think you have the absolute value, but I think because your interval of convergence is going to be from negative 1 to 1. We're going to double check here. Anyway. X can't be 0, but all right. But on the right side, say, what is this going to give you? Well, that's going to be the sum. If I integrate x to the n dx, that's still 0 to infinity. That didn't change. So this is going to be x to the what? N plus 1 over what? N plus 1. Don't forget that constant c. So what you showed is you have this function here. So the question is going to be now, you're going to say, well, what is this c here? If I go c, what is c? So what they do is they have a substitution. They'll say, okay, let x be 0 here. And if x is 0, we get minus natural log of 1 minus 0 is going to be that sum with, that's going to be 0 plus c is going to be c. Minus natural log 1 is c, or c equals 0 here. So here's the moral of the story. There was a minus sign outside. So this can be written as minus 0 to infinity x to the n plus 1 over n plus 1. So the point I'm making is if you can write a function as a power series, you can differentiate, you can integrate, you get other new power series functions.
The base shouldn't be 0 or 1. For the power, when the x, the power is n plus 1 x, and that would be 0.
Yeah, you're gonna have to change your domain here, right? X can't be what number? 1. Is that true? X can't be 1. That's true.
But for the power, the definition would be stuff. The base should never be 0 or 1. Maybe I did that wrong.
The base shouldn't be 0 or 1. Well, you can't be 1. I mean, can you let x be 0? X could be 0. X can't be 1. Anyway. And then here's something that the book wants to point out to people. Because you might say, I want you guys to know. I'm going to do kind of what the book wants to note here for this particular function here. And there's reasons. Okay, we're going to share with you guys. There's reasons here. What's our time like? If x is 1/2, I'm going to share with you guys something that's really interesting here. If x is 1/2, right? You can plug in 1/2 here for x. You get the natural log of 1 minus 1/2. Right? What's that going to give you? Plug in 1/2 for x. Minus 0 to infinity 1/2 to the n plus 1 over n plus 1, which is the natural log of 1/2 minus 1 over 2 to the m plus 1 times m plus 1. Double check. Is that right? And then, let me remind you guys of a little bit of something here. This is minus natural log of 2. Okay, because you can write 2 or 1/2 as 2 to the minus 1, and then you could use properties of logs. So that implies that the natural log of 2 is going to be actually positive now, because you got a negative and a negative here. Sum from 0 to infinity, 1 over 2 to the n plus 1, n plus 1. Now, what they sometimes do is they change the index. Because on the right side, if you let n be 0 and you start looking at some of those terms, you get 1 times 2 now, and that's n is 0. Now when n is 1, you get 1. It's going to be, oh, I switched the order on you guys. 2 times 1, this is when n is 0. Now when n is 1, so you get 2 squared times 2, okay? And so they can kind of write this a little simply, or simpler. 2 cubed times 3, this is when n is now 2. So sometimes what they'll do is they'll change the index to start at 1, and now they say, okay, let that be what? 1 over 2 to the k times k. Now, they want to change the index to k. Doesn't matter. But this is now a way to describe the natural log of 2. And the natural log of 2 now, you can describe really as this particular sequence. 1/2 plus 1/8, or this sum. 1 over 24, that goes on forever. And you might say to me, well, why do they even care about some of these things, right? Where are we really heading with this? Why do we even care to write functions as power series? Why do we care? Well, you can approximate the natural log of 2 with this sum, right? So if I said to you, is it true that the natural log of 2 is approximately 1/2 plus 1/8 plus 1 over 24, if I just take the first 3 terms? So if I just take my first 3 terms, notice this. Let's clear this out. Natural log of 2 is what you see here. If I take 1/2 plus 1/8 plus 1 over 24 here, okay? What you're going to start to see is I can start to approximate if I take more and more terms. This will be a better sum if I say, okay, what would be the next term then? K is 1, 2, 3, 4. So it's 2 to the 4th times 4. Okay, so if I said, okay, take the answer, second answer, plus 1 over 2 to the 4th. Where do we put the power key? There you go. 2 to the 4th now, come out of there, times 4. I just added the very next term. Don't I get closer to the what? Natural log 2. Let me take that answer, second, add the very next term. 1 divided by, now 2 raised to the 5th power times 5. I'll get even closer. So I'm getting closer to that value here. I just have to keep adding more and more terms, and I'll get closer. So here's the idea. The idea is we can approximate values here by just adding more and more terms. And that's really what your calculators are doing. That's not just true for what? Let's go back to the original geometric series, okay? Let's see why we started the day here so you guys know what I'm talking about. You see this geometric series we started with here? What are those terms? The terms of this series here is what? X to the 0, right? X to the 1, x2, x to the third power. Okay, that's 1 plus x squared and so on, okay? I'm just going to go up to x squared. So what I'm going to say to you guys is this is the function, and this is just the sum of what? The first three terms. Let's go to Desmos. Y equals 1 divided by, what was that? 1 minus x. And that's actually probably not a good example, but whatever. It's not a good example. 1 plus x squared. Well, it's kind of a good example. What's the next term, by the way? Would the next term be x to the third power, geometrically speaking? Say yes. I added another term. Here's my point. What does x have to be around? Between -1 and 1. Is that true? So around 0, here's what I'm saying. This is around 0. That curve in red is approximated with that sum of polynomials there, 1 plus x squared plus x cubed. You guys see my point? So we can approximate the function 1 over 1 minus x with that polynomial. It's not an infinite sum, it's a finite sum. You want a better approximation? Add x to the what? Fourth power. Now this is around 0. I'm just saying focus around what's going on around 0. Doesn't that curve behave very closely to it? Around 0, between -1 and 1. So right in the middle there, it behaves very similarly. Remember, the interval between -1 and 1 is right over here. This is what you're looking at. But the point I'm wanting to make to you guys is this. The reason we care so much about the power series representation, I just graphed this, isn't so that we get the infinite sum, really, but we're able to now approximate curves like this 1 over 1 minus x, this very simple curve, with a polynomial. Calculus is a lot easier to do with polynomials, like differentiate, like integrate, and perform limits. So you're heading into the world of what I say is approximation here. And that's really the essence of writing a function as a power series. Yes, you have the infinite series, and this is around a particular interval. This is that interval of between what? -1 and 1, but essentially around 0, because this is the power series representation here, x minus 0 to the n, this is that a value, right? So around that a value, you get to approximate that curve. You don't believe me? Take a look at Desmos and see what Desmos just did. The red curve is the function, and the blue curve is the sum of those terms. It's an approximation. Around 0. That's what we're doing around this number 0 here. Okay, you guys see the point? So this is why some of these things exist that you're doing, and your calculators take advantage of this. Technology uses this. This is related in some way to the linearization function. The linearization is just a polynomial of degree what? It's a linear function. Y equals, in other words, when you did calculus 1, this is all you can do. That linearization function. you can approximate the curve around 0 with 1 plus x. That's a linear function. Calculus 2 comes along, and you can approximate curves now with polynomials in general. If you notice, all of these power series representation of functions are polynomials. Is that right? See, this one, 1 over 3 plus x, this is a polynomial. So you're approximating functions with higher order polynomials. And ladies and gentlemen, we're going to do some more tomorrow, but I hope you guys enjoyed the lecture as much as I enjoyed giving it to you guys. But this is why, again, we do what we do with power series and why series converge and diverge. This is why you really care about these topics, is because they're used in your future. This is a very general, powerful topic that gets used in math and science settings. Trust me on that. You guys are really, in some ways, babies in the world of mathematics. You're just a baby. I'm talking months old. You're not even adults yet. You're not even toddlers. You're still infant babies, months old. This topic, because like I said, a lot of things build on these things. Anyway, we'll continue more tomorrow with this very powerful, wonderful idea. So I hope you guys enjoyed the reason for why you go through the pain. It's because it has a lot of powerful implications. Anyway, see you guys later. Some extra time there. So that's your final, that's your schedule. This is what's happening. So anyway. Okay, let's go over what we were seeing, because you can probably see this on your final. Some more power series expansions that we did. Let's kind of do a little review of one. For example, if they give you a function, so now we're writing a function. This is where we left off. We're writing a function f of x as a power series expansion. So you say, well, what's the function? Well, they give you 1 here over 9x squared. Okay? Now, I want you to remember what I gave you guys to use. What's going to be used in this scenario is if you have a function like 1 minus anything, it's the geometric series expansion. Okay, like that. And that assumes what you have here is less than 1 in absolute value. Right, so this is kind of what you're using here again. And, you know, and I could give you guys, I'll change this to a minus sign just because we already did a plus. You know, we already did a plus, but anyway, I even use the color green here. Okay, so here's kind of what you're going to use there. Right, so this is going to be here, 3x to the second power here. All right, so you're going to notice that 9x squared is what you see here. Okay, so we're going to write 0 to infinity now. So what's in that triangle is 3x. So you say, do I replace that triangle there with 3x? Yes. Okay, so that's 9x squared. That's going to be that 3x. So that's what's going to go in that triangle here. Now, again, you're going to use beginning algebra. Beginning algebra. That's 3n, x to the n. You're going to use properties there of exponents. So this power series expansion now for that function is what you see here. So 1 minus 9x squared is simply written this way. And of course, what you require is the absolute value of 3x needs to be less than 1, because this is what goes in that triangle here. And what that means is you got the absolute value of 3 times the absolute value of x, which is 3 absolute value of x. So you have convergence for the absolute value of x being less than 3, which means your interval of convergence here is what you have here. So here's my interval of convergence here. Negative 1/3, 1/3, and that's what we're looking for. Oops. Uh-oh. Sorry. Thank you. Okay, hold on. Sorry about that. Sorry about. Okay, let's go back. Let's undo this. You're right. Let's fix this here. I apologize to you guys. Let's fix this here. What goes in this triangle is 9x squared. So I apologize. That goes 9x squared. Okay. We got to wake up, get that coffee in us. 9x squared. Okay, good. So now we'll use our algebra skills, beginning algebra. Okay. So we get 9. I think we'll use purple. Apologize. 9n x to the 2n. We distribute the powers right. So 9 to the n, x to the 2n. There we go. I apologize to you guys. There it is. There's your power series expansion. And don't forget that constant there, that 9n. So you just fill that part in. I apologize. I'm just looking at different kind of examples here, right? So if you give you guys another example here, they say if your function is, let me change this now, 3 to the 1 plus x to the 4. They want the power series expansion here. You're going to use the same mechanism here, right? But we're going to have to write this as 3 times 1 over 1 minus x to the 4th. So now we're going to use that power series expansion here. You're going to replace this with the sum now, negative x to the 4th to the nth power, n is 0 to infinity. So you're going to replace this portion here with what you have here. Now the algebra, because you think of a negative 1 there, this is negative 1 to the nth power, x to the 4n. So this is 3 now times the sum 0 to infinity, negative 1 to the n, x to the 4n. And if you like, you can put your constant 3 right back inside the summation here. So there we go. Here's our power series expansion for 3 over 1 plus x to the 4th. Okay, now you say, but doesn't that assume the absolute value of, what's this? Negative x to the fourth is less than 1, and that is true. So remember, this is negative 1 times the absolute value of x to the fourth, which would be absolute value of x to the fourth has to be less than 1. Right? Which means, again, x is between negative 1 and positive 1. So there you guys go. So here's another power series expansion for these functions. And we kind of seen yesterday why you care, right? So if I go to Desmos 3 over, right, we've seen why we cared about this. Y equals 3 divided by, what was that, 1 plus x to the fourth, I think? Okay, so if we looked at the detail here about this interval of convergence here, right? So remember, they have this interval of convergence they talked about. Your book says it's the absolute value of x minus a less than that radius of convergence. So this is how they define the I. So in this case, this is like the absolute value of x minus 0 is less than 1 here. So that a value, this is around a, well, this is around 0 with a radius of convergence of 1. So you might say, well, why do you care? Like if I look at these terms now, start looking at some terms here. Let me erase this since it's in our notes. So if n is 0, we say, oh, that's negative 1 to the 0, x to the 4 times 0, there's the first term, plus 3, negative 1 to the first, x to the 4 times 1, there's the next term, if we start looking at terms, plus 3, negative 1 squared, x to the 4 times 2, you're going to end up with really 3 minus 3x to the fourth, looking at the terms. This is the first 3 terms. Plus 3 x to the 8th. So that function that's rational, just looking at 3 terms, I'm going to erase this. This is just some 3 terms. This is around 0 now. The reason I brought that up, this is around 0, is we can actually look at this graph, 3 minus 3x to the fourth plus 3x to the 8th, all in Desmos. Right, what was that? Plus 3x to the 8th. Okay, and we got to change that color. Let's make that one red, that's fine. The point I'm making is the blue curve around 0 is modeled by the polynomial there. Y equals 3 minus 3x to the fourth plus 3x to the 8th. Around what? Around that 0. So, just to kind of throw this out there, you might say, well, why do I care to approximate these curves? I'm going to give you guys a note. Because this is calculus. If they want us to integrate 3 over 1 plus x to the fourth dx, that integral is approximately the integral here of 3 minus 3x to the fourth plus 3x to the 8th dx. Okay? So polynomial functions, like what you guys see here, are a lot easier to integrate than maybe the function they originally gave you here, right? So this is kind of one of the reasons why you care about this, especially around that interval of convergence here. You can approximate the area under the curve for the rational function. That may be very difficult to integrate. However, this is a lot what? This is a lot easier. And as you guys can see in Desmos, that looks to be the case, right? You guys see the point? You're like, wow, I don't realize why it's so important to find these power series. Yeah, it's very important to find power series because you start to approximate various scenarios. And that's why it's kind of extremely important for you guys. And then let's give you guys some more. I don't think we did this yesterday. Maybe we did. I'm not sure. Did we do this one? Right? Did I give you guys the what about when the function here? I might have given this to you guys. What about the natural log 1 plus x? Did I give you the power series expansion from that? No, you got a power series expansion from this. We know this power series expansion. I think we did this one. Okay, so from the knowledge of this power series expansion, we can integrate say, isn't that natural log absolute value 1 plus x is a sum, because the integral of a sum is sum of integrals. And I can actually pull out the constant and just integrate right in here. And they say, what about that constant c here? All right. So yeah, I'm not gonna write it down again, but then you can say, well, what is c? I think your book likes to say, okay, well, let x equal 0, and we know natural log of 1 plus 0 becomes, everything over here is 0, is c, and natural log of 1 is 0, so c is 0. So you have the natural log really of 1 plus x sum 0 to infinity, negative 1 to the n plus 1. Okay, now similarly, if you said, okay, where are we going with some of these? If you had to integrate 1 plus x squared dx, since we can integrate these. Well, that's going to be the integral of the power series expansion for what you had here, 1 plus x squared. And I think we might have had that somewhere. If not, we can find that pretty simple. We can say, well, what is the power series expansion for this? Right? 1 plus x squared. That's 1 over 1 minus the minus x squared. I think we did this yesterday, which is the sum. Negative x squared to the n. And then by our algebra, negative 1n x to the 2n. So you can say we're just going to integrate here. Okay, so again, integral of a sum of integrals, pull out the constant, and you're really just integrating x to the 2n here. So this portion is going to be x to the 2n plus 1 over 2n plus 1, again, plus your constant. And over here, if you guys forgot what this is, that's your inverse tangent. Inverse tangent is the sum, negative 1 to the n, x to the 2n plus 1 over 2n plus 1, plus your c, and again, they're going to let x be 0. That gets your c as 0 here. Inverse tangent is going to be 0 to infinity, negative 1 to the n, x to the 2n over 2n plus 1. So you got these power series expansions again here. Okay, so let's note a few things about this. If I look at the first few terms for inverse tangent, this is going to be x minus 1/3 x cubed plus 1/5 x to the 5th. This is the first three terms. And remember, your interval of convergence is always the same as the interval of convergence for what you started with. So you'll have the same interval of convergence. I think this one here, I think we've seen this already, was at negative 1 to 1. So that means inverse tangent interval of convergence is exactly the same. We've already seen that. But if I went to Desmos and I said to you, can we approximate that curve around 0 for inverse tangent? Let's see what that looks like. Okay, y equals x minus 1/3 x to the what? Third power. When divided by 5, x raised to the 5th power. So remember, really between negative 1 and 1, the same interval of convergence, these curves are approximately the same. That's the whole idea behind this. And again, it's easier to perform limit questions, I should say derivative questions, you know, with these kind of curves here. So anyway, you might say, well, what do you mean? Right? So like, for example, they said, what's the limit? X goes to 0. Inverse tangent x over x. What you would do is use some of these terms here. X minus 1/3 x cubed plus 1/5 x to the 5th. So you might say, oh, does that make things nice and easy? Because every term now we divide by x, right? 1 minus 1/3 x squared plus 1/5 x to the 4th. We're supposed to take that limit. And we can see this limit's going to be 1. You know, this is kind of the idea. I'm sorry. Yeah, the limit's going to be 1, not 0. Apologize. Really got to wake up. But if I try to apply the limit to begin with, it was 0 over 0, right? So, you know, the power series expansions are extremely valuable for us. And let me go to my website because I updated some stuff for you guys. Like, for example, on your final, you might say, Mr. Judge, where are those cheat sheets? What I printed up for you guys here is the series summary sheet for your final. So hopefully people are paying attention to lecture. They know what's going on. They're not kind of random, inconsistent, right? They're like, oh, I'm working on integration right now. You know, oh, I'm working on how to integrate. I never learned that. What I made for you guys here is this summary sheet here. Look at this is the different tests for convergence. You guys are I'm gonna give you that for your final. You're gonna use this here, right? You guys see what I'm saying? It's a summary of all the different tests you guys have. I even have the geometric series, P series. Here we go. These are some of the power series expansions. Some of the geometric series expansions, a summary. Oh, where do you get the exponential? It's a Maclaurin series. We'll see. Where do you get the natural log? Well, we just seen one of these right now. 1 plus x, and you can even do 1 minus x, by the way, but whatever. So we can really start to dive into some of these different power series. Where'd you get sine, cosine, tangent, and some of the others? Right? So power series, as you guys can see, is a big topic. It's a big topic. Okay, so let's kind of look at some of these others if we want to try to see some of these things. Let me give you another one. Another good one before I move forward on this, kind of just giving you guys why you care about power series. Hopefully you guys see that. It really makes life easier. And then your book has this very, very famous example here. Another example. What if the power series they gave you was nice and complicated like this? Okay. This is a nice rational function, and you say, boy, Mr. Judge, that's pretty tough. Well, what do you think they do here for this rational function? They use partial fraction decomposition here, where they write the rational function, they factor that. This is factorable as 3x minus 1 times x plus 1. So they're going to write it here. They use partial fraction decomposition here. Just to kind of share with you guys where some of this stuff comes from. Now, by partial fraction decomposition, I can tell you A is going to be 1, B is going to be 2. You're going to go through your PFD process. That's pre-calculus, right? So that means you get 1 over 3x minus 1 plus 2 over x plus 1. So this function, f, is the sum of two simpler rational functions. So this is where this comes from. And then I kind of recommend to you, you say, well, what do I do with this now? You're going to start to write it as that geometric series I shared with you guys here. I always do that because I'm used to writing it that way. right? You're going to use this again. But the problem is, let's change the colors here. How do I write this? How to write this as power series? We're going to have a sum of two power series. So the first one in orange, just rearrange the term this way. -1 plus 3x. This is going to be the orange term. The other term, we're going to do the same thing. 2 plus 1x. Now, I can actually factor out, or I should say, however you want to think about it, I can multiply top and bottom here of the first one by -1, as long as it's the same term. So this is thought of as -1 over 1 minus 3x plus 2 over 1. We'll do that plus, this is minus the minus. So we can write this as -1 now times 1 over 1 minus 3x plus 2 over 1 over 1 minus x. So you're going to have that first fraction, the second fraction, but you're going to use this power series representation now for each. Anyway. Okay, so you say, is that -1 times the sum of 3x to the n goes to 0 to infinity, plus 2 times the sum, negative what? X. I started to do the algebra already. 0 to infinity. So this is 0. You get 3 to the n, x to the n. Don't forget that negative sign. Plus 2, -1 to the n, x to the n. 0 to infinity here. Now, all I did, because on the left, this first one, that's the orange, there's your green. I just rearranged the terms, so I start with a positive. I'm saying this will be 0 now. I'm going to put the constant back in like we've been doing here. And then minus 0 to infinity. Put the constant back in, -1 looks like. 3 to the n, x to the n. Okay. Let me double check. Oh, I'm sorry. Keeping it this way. Yeah, I'm going to leave it there. Okay, looks like we're okay. Now, remember, by property series here, I can write these under 1. Sum of the difference is difference of, well, take the difference of two series here. And then you can factor out your x to the n here. This is factorable. I guess I'll use pink. Okay, so if you say, oh, 0 to infinity, 2, -1 to the n, minus 3 to the n, x to the n. So that big rational function, right? So you say, let's kind of write it all together here. That 7, what was that? 7x minus 1 rational function, 3x squared plus 2x minus 1 can be described as 0 to infinity, 2 to the -1n, minus 3 to the n, x to the n. And we can actually kind of look at the terms there and see how that behaves. But anyway, so let's kind of note the interval of convergence, though. Right? What is the interval of convergence for this series? Well, we have two intervals of convergence, one for this first fraction in orange, one for the second fraction in green. So I'm going to write this down this way. Remember what this means, right? So in orange, the interval of convergence for the orange version is the absolute value of 3x being less than 1, and you guys know what that means. So I think we have what? Negative 1/3 less than x less than positive 1/3. Okay, I think we've seen that already for this one. Interval convergence. Now, what about the one in green? Well, the one in green is right here, right? We use negative x. So the interval of convergence for the green, absolute value of negative x needs to be less than 1. We know what that means. That means negative 1 is less than x, which is less than positive 1. So then you might say, well, what's the interval of both? Well, both is the word and. We need the intersection. And the intersection of these two intervals, negative 1/3 to positive 1/3, negative 1 to 1, the and intersection is going to give you simply negative 1/3 to 1/3. It has to satisfy both. So here's my interval here. The rational function, 7x minus 1 over what? 3x squared plus 2x minus 1. Let's take a look at this in Desmos. Okay. All right, let's going to write this rational function if I can. 7x minus 1. Okay, come out of there. Divide by 3x squared plus 2x minus 1. Okay, so here's kind of a rational function. The aspect ratio is not good for that, but anyway. Let's try to look at the polynomial version here. First few terms for the polynomials. Right? For the series expansion here. It's going to be hard to see. So I'm going to try. N is 0. Plug that in. You get 2 to the negative 1 to the 0. Okay. Minus 3 to the 0. That thing's going to be x to the 0. Plus 2 to the negative 1 to the 1. Minus 3 to the 1. X to the first power. Plus 2 negative 1 squared. Minus 3 squared. X squared here. Okay. So we're going to see the first three terms there. If you guys don't know, what is this going to be? I think that's 2 minus 1. That's negative 1. And this is positive 1. This will be 2 minus 3, is it? Negative 2 minus 3. Constant's negative 5, and that's just x. 2 minus 9 looks like it's negative 7 here. So we get negative 1 minus 5x. Double check. Is that minus 7x squared? We'll double check that. I'm not sure. I'm not awake. Negative 1 minus 5x minus 7x squared. Let's plug that in Desmos. Negative 1 minus 5 what? X minus, what was that constant term? 7x. Okay. So around, remember what we did, the interval of convergence, negative 1/3 to 1/3. That's really around 0. So the curves, in fact, do approximate each other in that little interval. And so in that little interval, if you wanted, you could differentiate, you can actually integrate and get a good approximation to the solution if you found that the rational function will be too hard to integrate. And that's why you start to care about the power series expansion here. Okay, first 3 terms. You want to be more accurate, take more terms. So this is the approximation in the first 3 terms, ladies and gentlemen. So it's kind of a good deal. Anyway, okay. Yeah. Yeah.
Just said that the first 3 terms is a good approximation. We're good.
Yeah, it looks like. Oh, I'm looking at first 3 terms, and yeah, it looks like the first 3 terms is pretty good. Yeah, but if you want to be more, you do go to 5 terms or something. It depends on how. There is going to be a formula for what we call the remainder or the difference. So there is an accuracy formula that you can dive deep into to try to be accurate within a certain place value. So there is a way to do that. And I think it's even written in your book. They do like a remainder theorem on it. But I'm just kind of sharing with people why you care about these. Because the picture is worth 1,000 words. You know, you're like, wow, I can see why they care about that interval of convergence around 0, -3 to 1, you know, because that interval of convergence again, right? When you go back and go, what does this mean? Well, what does your book say? Your book says, oh, the absolute value of x minus a less than r. What does that mean in this case? Well, it means around 0 and the radius is 1/3. Because this is how you describe that interval. Oops. Between negative 1/3 and positive 1/3. So around 0 with the radius of 1/3 for that interval of convergence, this is why you care about finding that interval of convergence. Don't just say, oh, we could do that for any x value. No, you can't. It's only around that a value or around 1, okay? So this is why the interval of convergence is always an extremely important detail. And it will be, if you look at the details here in the sheet I gave you guys, they're going to always describe the convergence for absolute value of x less than 1. So you can only describe it for x around 0 because the radius of convergence is 1. And all the others, this is good for all x. This is good for, you know, absolute value, you know, for the various x values. You can actually come up with these as well for sine, cosine, tangent, secant, inverse sine, inverse cosine, inverse tangent, even hyperbolic functions. A lot of functions have your various interval of convergence, the values of x in which it's valid. So that's why the book wants to always give you that kind of interval and, you know, reference. But I kind of share with you guys what that means so you guys can see it graphically. Because we can look at a lot of different versions of this. But eventually what happens is, I mean, even inverse tangent, we can even describe that. Like, for example, I have, you know, we looked at inverse tangent. What if they said they want the power series expansion for a function like this? Inverse tangent of maybe 3x, right? What's the power series expansion? Well, I think we derived, I showed you guys what that expansion is. I'm just going to say x here, okay? And let me go back and remind you guys, we derived it. It's in the notes. I can kind of, here's inverse tangent. If you guys remember, it's the last one. 0 to infinity it was alternating -1, yeah, x to the 2n over 2n plus 1. Now remember, this is for the interval is the absolute value of x less than or equal to 1 for inverse tangent here. So if I go back now and you say, well, what happens in this case? Well, how I think of it is I'll put that triangle again here. That triangle again here. Okay, and so whatever you have as an input, in this case, it's what? 3x. This is really the triangle again. Okay? Just replace this with your 3x. Replace this with your 3x. Replace this with your 3x. So if you already have that power series expansion in general, you can write this as the following. The only thing you want to do over here is some of the algebra. So algebraically speaking, you say, is this 3 to the 2m plus 1, x to the 2m plus 1 over 2m plus 1? It is. So the power series expansion now here for that curve, -1 to the n, and we're running out of space. 3, 2n plus 1, x to the 2n plus 1, which is odd. And then typically they just put the constant together here, you know. And the absolute value here for your interval of convergence now, again, will give you the absolute value of x, here being less than or equal to 1/3, which is, again, around 0, if you want to think of it that way. Here's the interval of convergence again. So around 0, you know, you have, maybe we'll just use this. This is your power series expansion. Right? And then I'm going to give you guys a note, because sometimes they do that. They'll do this to you. What's the power series expansion if you have the function going to be x squared, maybe inverse tangent 2x? Power series expansion for those. Well, all you would do is what? For x squared, just replace inverse tangent 3x with what it is in terms of the power series. Sum 0 to infinity, -1 to the n, 3 to the 2m plus 1 over 2m plus 1, x to the 2m plus 1, and there's an x squared there, right? So just put that in inside your summation. X squared times x to the 2m plus 1, and this would be over that 2m plus 1. You're just using beginning algebra, right? This is just beginning algebra. So just use properties of exponents. 2n plus 1 plus 2, that's 2n plus 3. So the power series expansion here is what you see. It's not 2n plus 3 now. You just have that factor x squared there. So, I mean, you might say, wow, you know, I'm not going to go into decimals. I'm just kind of curious here. X squared inverse tangent 3x around 0. I mean, that's the curve. It's kind of interesting. It looks like a polynomial. We can, if we did, I mean, I might. Gosh. Let's look at the first three terms. When n is 0, n is 1, n is 2. Right? N is 0. Tell me, I'm just going to do it mentally. That's 3 over 1. That's x cubed, by the way. It's when n is 0. Now, n is 1 minus 3 to the 4th over 3, because n is 1, x to the 5th power. Now n is 2, so it's plus negative 1 squared, 3 to the 2 plus 1. Wait a minute. N is 1. That's 3 squared. See? Not really awake. This will be 3 cubed. N is 2. 2, 4, 5. Odd powers. Then 4, 7. So I'm just going to kind of do a little bit of the arithmetic. I'm kind of excited here. Okay. So let's double check. This is what I'm saying here. If I'm correct with my arithmetic, by looking at the n values, n is 0, n is 1, n is 2, first three terms, let's see if we can approximate that curve, 3x cubed minus 3x to the 5th. What was the end? 9x to the 7th. So the curves are approximately what you see. And I don't remember that interval of convergence here, but anyway. So around 0, really around 0, close to 0, the curves are practically the same. Is that right? Can you see that? Around 0? Boy. So you're approximating curves with polynomial functions. And polynomial functions are easier to perform calculus with. Anyway. So I'm kind of excited about those when I see them, and you have a lot of different things you could do with that. Yeah, there is a lot you can do. So anyway, let me just get my notes kind of together here if I can. Okay. So now you say, well, what about this section what they call Taylor and Maclaurin series expansion? Well, remember this. If we look at the general definition, Cn, let's try this. Cn xn from 0 to infinity, okay? Which is C0 plus C1x C2x squared, and that goes on forever. And if we looked at even more terms, just to start this off, C3x cubed, and that goes on forever. Okay? So if we can write a function as a power series, if it can be done, then I want you guys to note the following. Let's note this. F prime is the derivative of f. If we take that derivative here of that power series expansion, C naught, C1x, C2x squared, and so on here, by properties of derivatives, you're going to get C1 plus 2C2x plus 3C3x squared, and so on here. And if you let x be some a value, and you say, where's that going to come from? Well, it's going to be x minus a over r. Just so you guys know, that means f prime evaluated at a is C1. This is going to be an important detail. Now, similarly, if we take the second derivative of the function, C1, 2C2x, 3C3x squared, that goes on forever. You say, is that going to be 2C2 plus 6C3x and so on? The answer is yes. And what we'll find again, if we let x be a, we're going to get f double prime of a is 2C2. Sorry. Where are we at? Sorry, this is going to be 0, not a. I apologize there. I'm like, wait a minute, this is a bit odd. Around 0. X, this is going to be around 0, not a in general. This doesn't make any sense. So I'm like, wait a minute. Okay, now it makes sense. Sorry. Okay. And so I want you guys to know something here. This means that C2 will be f double prime is 0 at 2 if we solve for C2. And then that's the kind of idea. Now, if you continue the process forever, not really forever, if we continue, you're going to get the third derivative evaluated at 0 will be 6 C3, where C3 is the third derivative evaluated at 0 over 6. And if you continue forever, here's what you guys are going to end up with. You're going to end up with that Cn, which is the coefficients, is the nth derivative evaluated at 0 over n factorial. Okay. That's an important detail, because we're describing Cn here. So what that means for us is this. Your function in general, if it can be written as a power series, we can write it as f and evaluate at 0 n factorial for x around 0. And don't forget the x to the n. Similarly, and I know we're out of time, but we're going to see the examples tomorrow. If you have your function around A, remember the general power series definition around A. What you can see, and this is where they're going to give you the x minus A less than R, you're going to get, with the same exact process, Cn going to be the nth derivative evaluated at A n factorial. And again, for x equals A in this case. So you have, this is known here, by the way, this last one is known as the Taylor series expansion. And then you have the Maclaurin series expansion. So this is your Taylor series expansion. If I can get the iPad to cooperate. This is Maclaurin series. Maclaurin series. And so, ladies and gentlemen, you might say, well, how do I use that? Well, the standard first example that they give you is the exponential function. The reason is simple. Is because when you take the derivative of this function, it's e to the x. It's always e to the x. The nth derivative is e to the x. So if you want to see the power series expansion around x is 0 now, okay, you can replace this x with 0. Here's what this means. This is e to the 0 forever, which is 1. Now you say, why is that important? Because what is the definition of Cn? In our case, Cn will be 1 over n factorial for all values. So that the exponential function here can be simply written as x to the n over the n factorial. Now, if you said, why in that summary sheet you're going to let us use, why do they say for all x? Right? They're going to say this is converges for every x value. This is the exponential. Converges for every x value. Well, what you would do now, in case you guys wanted to, simply use the what? Use the ratio test. And you'll get convergence for all x. And you may not realize it, but I think we probably did this one. So here's your power series expansion for e to the x. Now, does that mean we can describe this when x is 0, this is 1, this is when x is 0, x is 1, this is x is 2, 1/2 x squared. Notice this if I took the first 3 terms. Around 0, let's see what happens with this in Desmos. Okay, you say this is y equals what? 1 plus x plus 1/2 x. Around 1, we're starting to see something. Maybe I made a mistake. I don't know. Maybe we need more terms. Plus 1 divided by, oops, I'm sorry. I made a mistake. That's what it is. There we go. There we go. I made a mistake. That's not good to make a mistake. Let's make that color, though, red. That's what it was. I didn't change the power. It's like, what happened? So the purple curve is e to the x. The red curve, and look at this around 0, ladies and gentlemen. The red curve is the polynomial functions 1 plus x plus 1/2 x squared. So we're diving into Taylor and Maclaurin. We'll see some more tomorrow on the what's tomorrow? Thursday, the very last day. But, you know, we did Power Series again and introduced Taylor and Maclaurin series for you guys. But as you guys can see, this is really good stuff because, you know, we can even do, for example, if they wanted you to write the Power Series expansion for the function e to the x squared, right? Well, you just have to replace x with x squared. And we get the Power Series expansion. X to the 2n now, and factorial. And that's also good for all x, right? This was good for all x. All real numbers. So, you know, we can maybe find this to be something if you had to integrate, because you can integrate e to the x. But, you know, what if you had to do an approximate integration for this, which you can't integrate? You just can't integrate this e to the x squared. That's a whole other problem. That's a whole other thing. You cannot integrate e to the x squared. Okay, but around 0, because that's what x was around 0, we can approximate that with some of the terms here, right? If you want to do the first 3 terms of that series. So around 0, we can do that approximation of this integral if you like. You can even differentiate it and all that other stuff, you know, so even evaluate, you know, if you had to, you said, hey, how do I evaluate e to the maybe 0.1 squared? Well, you would use the Power Series expansion, maybe the first 3 terms. That's what calculators use. They use Power Series expansions. Anyway, we just kind of started that, and let me say to you guys, I hope you guys enjoyed this. I can keep going all day long. I could really keep going all day long with this stuff because it's like, wow, now we're finally get to something good and something very interesting. And that's how I see it. Anyway, okay, I hope you guys enjoyed the lecture. Again, your homework is on some of that Power Series that you guys see here. We said homework. I'm learning how to integrate. I'm back at U sub. What are you talking about? I'm doing the stuff you asked me to do in the first week. I'm still there. What do you mean? We got some